Alright, so this is take number 2 on the strong acid, strong base stuff. This is really not all that difficult, so this section should not take very long. Basically, we just need to talk about a little extension of the concepts that we were talking about before with pH and molarity and how to calculate pH and how to use the pH to calculate the H plus concentration, all that stuff. Okay, so we'll start with strong acids. First off, there are 7 strong acids listed here and in your book. There are 6 strong acids listed on the AP curriculum. The one that they don't include is the HClO3. That's a bad circle. The HClO3. The chloric acid. Okay, so I would assume that because they're not including it in their curriculum, you're probably not going to be expected to know it on the AP exam. But I want to mention all 7 just in case, because chloric is usually considered to be a strong acid. Okay, so we talked about these in an earlier unit, Unit 3, I believe. So you basically just need to remember these. I told you that then, I'm telling you it again now. You need to know these 7 strong acids, because everything else, every other acid we deal with is a weak acid. And the way you're going to know it's a weak acid is because it's not one of the 7 that you memorized. Alright, so you need to know these. What it means for something to be a strong acid is when you put it into water, it's going to completely dissociate. Okay, in other words, exist totally as ions, be a strong electrolyte. So you put HCl into water. Whoops. Sorry. Put HCl into water, and it dissociates into H plus and Cl minus. Okay. Every time. Okay, and that's why we consider it to be a strong acid, is because it will always completely dissociate. Alright, so that makes these calculations really easy, because I don't know if you remember this from earlier in the year, but with a strong electrolyte, like, it could even have something like sodium chloride, we talked about if we have a 1 molar solution of sodium chloride, then when it breaks apart into its ions, now you have a 1 molar concentration of Na plus and a 1 molar concentration of Cl minus. Okay, same thing up here. If we have a 1 molar solution of HCl, that means we have a 1 molar concentration of H plus. Now what that also means, because what H plus ultimately does is it comes over here and attaches itself to a water molecule to form H3O plus, hydronium. Okay, now notice this is all 1-to-1 stoichiometry. Alright, so if we have a 1 molar concentration of HCl, that breaks apart. Now you have a 1 molar concentration of H plus. Okay, for every H plus that you have in the solution, it's going to find a water molecule and form an H3O plus. So then we also have a 1 molar concentration of H3O plus. So to say that we have a 1 molar concentration of HCl, I keep pulling this thing down, is basically the same thing as saying that we have a 1 molar concentration of H3O plus. Okay, so that's why they say down here for the monoprotic strong acids, H3O plus equals the concentration of the acid. They're equal to one another. Okay, now that works for monoprotic. I don't know if you remember this, and we'll talk about what monoprotic means in just a second, but if you remember this from the 3rd unit, if we've got something like Na2S, okay, when that dissociates, now you've got Na plus, and S2 minus, right? So if you have a 1 molar concentration of this up here, you actually have a 2 molar concentration of Na plus now. Alright, so that whole 1-to-1 relationship right here only works if it's a monoprotic acid. Now, you probably don't know what monoprotic means, or maybe you can figure it out just by looking at the word. I mean, mono obviously means 1. Protic sort of looks like proton, okay? And if you'll remember, earlier in the unit we talked about H plus is basically just a proton, because it was a proton and an electron. That's all hydrogen normally is. If it gives away its electron, now it's just a proton. Alright? So monoprotic, in other words, acids that only have 1 H in them. Now you can see from this list, H2SO4 is the only exception to that. Alright? So this rule right here does not really apply to H2SO4. It applies to all the other strong acids on the list. We will talk about H2SO4 in the next section. Okay? So don't worry about that for now. Everything else we're going to talk about in this section, we're basically talking about these these acids right here, okay? The ones that only have one hydrogen that they can give away when they get put into water. And it makes the calculations really easy, okay? So an example here, what is the pH of a 0.040 molar solution of HClO4? This is sample exercise 16.8 in the book, so I'm just going to walk you through this. So again, just remember, we're given the molarity of the HClO4. Well, when this gets put into water, it's going to break apart into H plus and ClO4 minus. Okay, so we also have a 0.040 molar concentration of H plus. All right, because it breaks apart in a 1-to-1 ratio. There's only one H that can break off of here. So that makes it really easy, because to calculate the pH, all pH is the negative log of the H plus concentration, or the H3O plus concentration, however you want to look at it. Alright, so then all you have to do is take the negative log of 0.040, punch that in your calculator, and you're going to end up with 1.40 for your pH. Okay, and that's it. It's as easy as that. Now a couple of things to watch out for here. First of all, you might be tempted to just say 1.4 on your pH, because that seems like two significant figures. Just keep in mind, the sig figs are the ones after the decimal point for pH. This first number is basically just a placeholder. Not so much a placeholder, I guess, as it signifies what the exponent is. Okay, so that first number we don't count as being a significant figure. So there were two sig figs in the original number up here, 0.40. So we need to have two sig figs in our answer. Okay. The other thing to notice here is it's always good to kind of check yourself at the end. So we got that the pH is 1.40. That's a low pH, all right? And when the pH is low, that means we have an acidic solution. It kind of makes sense that HClO4 would make an acidic solution, since it's one of our strong acids. Okay, so it's always good to just check that. If you end up with a high pH on this problem, you did something wrong. Okay, and you could know that just by looking at it. So, all right, so let's skip ahead here to the strong bases. There's not a lot of extra to these. These, I wouldn't say you necessarily have to memorize them, because you can just kind of remember a rule. And the rule is the soluble hydroxides, okay? In other words, the hydroxides that will dissolve when you put them in the water. So the alkali metal hydroxides, remember, pretty much all alkali metals are soluble, okay? So any of the group 1 metals, when you put it with a hydroxide, like sodium hydroxide, sorry, I really gotta stop doing that. Sodium hydroxide or lithium hydroxide or potassium hydroxide, any of those in group 1, those are going to be strong bases, because when you put them in water, they're going to completely dissociate because they're soluble. Okay, and the heavier alkaline earth metal, so calcium, strontium, barium, basically calcium down on the periodic table. And the reason for that, beryllium hydroxide, which is BeOH2, and magnesium hydroxide, MgOH2, are not very soluble in water. Okay, so if we have a, say we have a 1 molar concentration of this, that does not necessarily translate to a 1-to-1 or even a 1-to-2 stoichiometry for your hydroxide there, because not all of the hydroxide is going to dissociate, because these aren't very soluble in water. So that's why it's got to be the soluble hydroxides. All right, so I don't think that's going to be all that difficult for you to remember, but those are the strong bases that we typically talk about, okay? And these are going to dissociate completely in aqueous solution. Now, we're going to go back to a problem here and show you something you got to watch out for. But these are pretty easy too. So the pH of a 0.028 molar solution of NaOH. Alright, so again, put this into water, it's going to dissociate into Na plus and OH minus, and it's a 1-to-1 dissociation here, so the OH minus is also going to be a 0.028 molar concentration. Alright, so here's where you have to be a little bit careful, because it might be tempting to say that pH equals negative log of 0.028, okay? But the pH equation is the negative log of the H plus concentration, not the OH minus concentration. So there's a couple of ways you can do this. You could use the the Kw equals H plus concentration times the OH minus concentration. So the H plus times the OH minus concentration, and Kw is always 1 times 10 to the negative 14th. Okay, so you could use that basically to figure out what the H plus concentration is. Okay, so then plug that in, negative log of whatever you end up getting there. That's one way to go about it. My preference is a different way, and I think it shows both ways in the book. My preference is to start with the POH. I think this is just easier. Okay, so the POH is the negative log of the OH minus concentration, and we have the OH minus concentration, so we just take the negative log of 0.028, okay, which is going to give us where is it? 12.45. Okay, so that's our POH. Now, what you have to remember here, I'll write this up at the top here. 14. When you add the pH and the POH together, they should add up to 14. All right. So basically, to solve for the pH now, all we have to do is take 14 minus the POH, which is 12.45. And that's going to give us the pH of where am I? Lost my place here. Oh wait, I'm sorry. I was looking at the wrong thing. The POH, I apologize, is 1.55. I'm trying to do this just by looking at the book so I don't have to actually do the calculations. If you take the negative log of 0.028, you're going to get 1.55, not 12.45. Okay, so then you're taking 14 minus 1.55, which should give you 12.45 for your pH. Okay. Now again, it's always good to check at the end to make sure that you're on the right track here. 12.45 is a high pH. We would expect a high pH if we have a basic solution. Well, NaOH is a strong base, so it makes sense that the pH would be high. So let's say that you made that mistake I talked about at the beginning, and you just plugged in, instead of the POH, you thought that you were finding pH here, and you end up with 1.55, you think, for your pH. Then if you just check your answer, and you say, okay, pH is 1.55, that's a very acidic solution, does that make sense here? And you would see, well, no, I've got sodium hydroxide, that doesn't make sense. And then hopefully that would remind you of what you did wrong. Okay, so let's erase some of this, and then I'll show you part B on this one. Sorry, this is very tedious. I know there's got to be a better way to do this, but I haven't figured it out yet. No, you can't hold down the button. That doesn't work. Okay, so then the second part, it's asking for, well, what if we have a 0.0011 molar solution of calcium hydroxide? Now, here's where you have to be a little careful, because, like we just talked about, this is not a one-to-one dissociation. That's supposed to be a minus sign. Still getting the hang of writing with this thing too. So we've got two OH minuses here, which means if we start out with a 0.0011 molar solution of the whole thing, calcium hydroxide, there's going to be twice the concentration of OH minus, because once it splits apart, now you have 2 times as many OH minuses as you did of the original molecule. So your overall concentration of OH minus for this one, you have to multiply this 0.0011 by 2. So 0.0022 molar is now your concentration of OH minus, and that's the one place you have to be careful on this one. Then you're basically doing the same thing as you did before. Whoops, sorry. POH is equal to, and I really do think this way is faster, negative log of 0.0022, which when you punch that into your calculator, should give you 2.66 for your POH, and then you take 14 minus that number, and that gives you 11.34. Okay, and again, I didn't mention this in the last one because I was flustered by getting it wrong, but 11.34 has 2 sig figs. Only the numbers after the decimal matter. Okay, our original number here, 0.11, also has, or 0.0011 also has 2 sig figs. All right, so our sig figs are good, and then just checking our pH. This is it should be a high pH because we've got a base here, so that makes sense. All right. Okay, that's pretty much all there is to this one. So we'll call it quits, and hopefully the writing will show up on this one. You guys can use this to study. See you in class.